I'm not able to unmute them, so I'm going to read them. So the first one is that if we consider the Newtonian analog of the procedure you outlined at the end, that is, we have to charge fluid balls where the charge densities follow the mass densities. The requirement that the product of the charges equal the product of the masses is the same as the requirement that there be no net force on the fluid elements. Perhaps I am missing something, but it seems that what was shown is that with no net force, there is no net tidal force. What am I missing?
Let's see if I understand. I'm reading the question too, so I'm trying to understand.
Yeah, you can also read the questions, and questions, and yeah.
Right. Okay, so the product of the charges equals the product of the masses. So for me, of course, that guaranteed that the center of masses could be assumed to be not moving. And here, the question says that there's no net force on the fluid elements. So, yeah, maybe that's true in Newtonian physics, but I don't think it would be true in the relativistic situation. So I think there's no real, connection between the no net force requirement and the no tidal force result that you seem to get in this case. So I think that link would not be there, in GR.
Mm-hmm. Yeah, makes sense.
And you could have a different arrangement of charges. So you wouldn't have to have the charge to mass ratio to be constant throughout the body. So in that case, there would be differences in forces even within the body. So so I think there's more generality going on there. Yeah.
Okay, there was another question about the generalization of your results to rotation, to rotating systems.
Right. So there's been a lot of discussion about love numbers for rotating black holes, and it was confusing for a while. But I think a consensus has emerged, and there's a distinction to be made between love numbers that would appear in the conservative dynamics of a binary system. So those would be the tidally induced multiple moments. And for those, the love numbers, even for rotating black holes, would vanish. There's a distinct class of love numbers that would show up as dissipation. So that has to do with the tidal heating or the tidal torquing of a black hole, where you can actually change the internal state by either changing the mass or changing the angular momentum. And those love numbers that are tied to dissipation are not zero for rotating black holes, and they're not zero for Schwarzschild black holes. So I think that's how it goes.
Okay. Well, thank you very much for answering these two questions.
You're welcome.
A question for Robert Wald. This one was by Alexandra Brosius. She had a question about the current, so probably what we can do is that, Alexandra, if you're there, you can unmute yourself. I'm going to allow that right now, so you can do that.
Hi, thanks. I was wondering what the definition of currents is that you use, because there are a couple different ways you could think about currents in algebraic geometry and in physics. So I was wondering if you could explain that a little bit more. Thanks so much.
Oh, okay. So I use, as I recall, I use the term current for symplectic current and another current. I'm just using it in a, I'm working with a three form rather than a vector field, but if you dualized it to a vector field, I'm using it just to mean some vector field that would be conserved, that is divergence free, at least when equations of motion are satisfied or some other conditions hold. There was no, deeper meaning beyond my terminology there of, it's typical in physics to use the word current for some quantity that's going to be conserved under certain circumstances, if not always.
Thanks so much. That's what I thought, but I just wanted to check. Thank you.
Okay, so I don't think there are any other questions. Just checking the list of questions, but yeah, I think we went through all of them. Yeah, the number of attendees is way lower now. It's like 1/4 of the, so we lost many people, probably due to time zone issues. So if that's what we were talking with Matt, that it's very late in New Zealand, right? So
There is a question from Shinji, I think.
okay.
Can I ask a question?
Yes, of course.
So yeah, I already asked the question to Eric, but I forgot to ask. Ask the answer. I think I asked whether it is possible to consider a pair of extremal black holes as a test of your universality. But and you said yes, but I forgot to ask the answer to this question.
Yeah, well, I didn't have an answer because I didn't do the calculation.
Yes. What do you expect?
I would expect that the result would carry over, that it would be the same story. But I should really do the calculation, because if it turns out not to be the case, then I'll have to rethink everything. So yeah.
Okay, yes, I look forward to the result. Thank you.
So I have a question for Richard about the evolution. You were mentioning essentially the evolution, the different phases of the evolution. Where you first have the instability, right? Then you have a cloud of the fields on the black hole, and then you have the emission of gravitational waves. Is this? I mean, has this been calculated like in different, like doing different approximations for the different phases, I guess,
Right.
or there is like
Yeah.
is there like a whole simulation of the whole process? I don't know what's
Yeah,
the status of that.
Well, the part that I've been involved was using some approximation, so basically to perturbation theory. So where you basically consider first you do you compute the estimated time scale using like perturbation theory, so a test field in a curve background, and that then using, for example, an adiabatic using adiabatic evolution, so you write down m dots equal to the fact that you have a flux at the horizon because of this difference of this field. And so there's a way to do it, and gravitational emission, then you can do it also using perturbation theory. So you have you consider the fact that you have a stress energy tensor that is generating gravitational waves, and you can, for example, use Tchaikovsky's equation with some source, where the source will be the scalar field, for example, sourcing gravitational waves. But there's been also completely numerical simulations where what they did was to consider vector fields in this case, just because time scales are shorter, so it's easier to simulate. And they only simulated up to the first phase, so they only saw the black hole spin decreasing, the spin going to this field, being transferred to the field, and they also computed the gravitational emission. So this is work by William East and also Franz Betorius, and so it's from I think 2-3 years ago. But yeah, I mean, there's some work on with vector fields where they actually did the whole an evolution that shows that actually the picture that I showed seems to be the correct one, at least in time scales that are relevant for astrophysics, like the full evolution on instability. If you more in academic for academic purpose, in the sense of trying to understand what happens if you wait an infinite time and you see what happens to each m mode that becomes unstable in an infinite time. That I think is an open problem actually, to understand what is actually is the end state, the final real end state of the instability.
Okay, thank you. I get a notification that there's a question, but I don't see it. I'm just trying to find it. Okay. No.
There's 2 questions in Q&A.
Yes. yeah, no, that's the. So there's a question for Robert Wald. I'm going to essentially allow Sai to speak. You can unmute yourself.
Hi.
Yes, we can hear you.
Okay, so I have a question. Why the second order equation decouples from the first order equation you showed us? For example, why we don't see the square of first variation of field did not appear in your second order equation?
Yeah, no, it very much does appear. In fact, the canonical energy, I mean, the canonical energy was a key component of those equations, although I just put a script E for that in there. But if you go back to the definition of the canonical energy, it's purely quadratic in the first order quantities. So, I mean, you can compute that, in fact, just knowing the first order perturbation. So anyway, the equation does contain, first order, quadratic in first order quantities. In particular, the canonical energy is playing a key role in that equation. But for the mass, it just has the second order variation of the mass, which is what we wanted to compute.
So do you have intuitive explanation for that?
Well, it's not, I think the equation does have a mix of first order and second order quantities. So it's not surprising or something, it's not, we've collected the most important quadratic in first order quantities into this canonical energy. But there's nothing surprising about the nature of the equation.
Yeah. Thank you.
Okay, the next question is for Eric Poisson. So it's from Tan Liu. I'm going to allow you to unmute yourself in 1 minute. Just as soon as I find you. Okay, now you can do that.
Hello. I have two questions about the tidal knob number. The knob number is defined for a spherical body in the slide of Poisson. Can this be defined for an irregularly shaped body? The second question is, when the Newtonian tide is extended to general relativity, only the TT component of the metric is involved. What about the other components? Thanks.
Okay, so about your first question, so you're asking whether you can define love numbers for bodies that are not spherical to begin with, and the answer is yes. So first of all, you would need to have some stellar physics that would allow you to have bodies that are not spherical if you're not, perturbing them in any way. And of course, real stars tend not to be, perfectly spherical. So in that case, what you would do is to try to distinguish, you would have multiple moments for your star. And part of those would be given by the initial irregular shape of the body, and part of it would be given by the tidal deformation. So you would probably try to define love numbers in terms of the difference between those two multiple moments. So that's probably how you would do it. But you're right. Typically it's done with bodies that are taken to be spherical to begin with. And for your second question, so in my talk I only showed the TT component of the metric, but of course, if you want a full description of the space-time, you have to calculate all the components. And if you look at my papers, you'll see everything listed. But I didn't want to show all of that because it's technical mess.
Okay, thanks.
Thank you. I had a question for Bob, if you would allow me.
Yes, please.
I will certainly allow you. I imagine the conference organizers will as well.
Yeah,
Well,
no problem at all.
I don't take it for granted. So I don't know if you saw it. I think it was a couple of weeks ago, maybe 2-3 weeks ago, there was a paper on the archive claiming that they had done source and Wald, but not to second order, but to third and fourth, and iterated it to any order. Have you seen this?
No, I haven't.
Okay.
Maybe.
I won't be able to tell you what they did and how convincing it is. But you may want to take a look. And my impression was that, well, it seemed, so to take a first variation to me seems doable. To take a second variation is a lot of work. To do a third variation to me seemed, unusually cruel. So anyway.
I agree. If they're just doing some straightforward perturbation theory, second order is about as far as I would want to go personally.
But anyway, so it's probably worth
well, thanks for alerting. Do you know who the authors are? Or
no, I just saw it passing, and I think I read the abstract, and that's as far as I went. But I'll email you if I dig it up again.
Yeah, well, I'm sure I'll be able to find it. Thanks for pointing that out.
Okay, thanks.
So there is another question for Robert from Charlie Robson. You can unmute yourself and ask the question.
Hi, can you hear me?
Yes.
Okay, great. So yeah, I had a question about whether or not extremality can be reached in a black hole spacetime. So in terms of the topology of the spacetime, there's a as it were like a violent shift in the topology when extremality is reached. One characteristic quantity that changes is the Euler characteristic. So for example, the topology changes when extremality is reached, and this is reflected in the Euler characteristic vanishing when extremality is reached. Do you think this has any role in kind of preventing extremality being reached? Although how this relates to the physical argument, I'm not sure, but it seems like there is like a violent shift in topology at the exact point when the charge becomes extremal.
Okay, so I'm not sure I know what you're referring to with the Euler characteristic. If you look at the extended, Reissner, Nordstrom, and or more generally charged Kerr space-times, then there is a drastic change, but if you're just looking at the outside of the black hole and maybe a little ways inside the horizon, and you're looking at a black hole, formed by gravitational collapse, then I would argue there isn't, a drastic change there. So I'm not sure. The topology of the horizon is spherical, so I'm not sure what you mean by, or you're talking about the Euler characteristic of the space-time itself.
Yeah, the space-time. The whole space-time.
Yeah, but I would argue that that's that's the extended space-time, not the sort of physical space-time you'd expect to get from a gravitational collapse. So I wouldn't, consider, if you just go from Schwarzschild to add a little rotation to go to Kerr, the maximally extended space-time changes drastically, but the physical space-time, well, it does change when you get near what would have been the singularity, which now will be a Cauchy horizon. There may be drastic changes near what would have been a singularity, but there are not any drastic changes, outside the black hole or a ways inside the horizon. Now, as to whether extremality can be reached or not, I'm not quite sure how to, sort of in principle, yes, in practice, no, I think is probably the answer I'd give to that.
Okay, I see. Thank you.
So just to continue with the question that I asked to Robert during the talk. So then there are no works analyzing whether or not average energy conditions are enough to. So I mean, I don't know if. So you said that there are no results on that. That you're.
Well, I myself have not thought about it, and I'm not aware of anything being written on that for this, particular instance. There's certainly papers that consider what aspects of singularity theorems or other stuff could be weakened. So yeah, I expect there would be, I'm sure there would be a weaker version that doesn't require that the average null energy condition holds, but whether it holding on all complete null geodesics or something, just on all complete null geodesics is sufficient isn't obvious. You may, if you have it holding on horizon generators, then that will certainly be enough, because all that comes into this is the integral over the horizon of. But those generators might not be past complete and all that, so I'm not, I wouldn't want to make some claim that you do only need that, but.
I see. Thank you.
I have a question.
Okay.
Can I ask a question?
Who's talking? Stefano.
Yes, it's me. Can I? I have a question for Bob. Bob, just something that occurred to me while you were talking. I mean, it looks like your demonstration doesn't rely at all on the fact that the geometry is singular inside. Now, normally we have this idea that you need to protect the singularity from being seen. But I'm correct that basically your demonstration doesn't rely on the internal structure. So it would work even if somehow there is a regular black hole, even if inside there is no singularity. Is it, or I'm missing something? Can you tell me this?
No, I mean, no, that's right. I mean, the analysis is done entirely outside the black hole, up to and very much including the event horizon, but we never look at anything inside the event horizon. So you could replace the interior with anything you want, and it wouldn't affect our argument.
So, in a sense, can we say that this is, I mean, we can imagine that for some quantum gravity regularize the singularity. It seems to say that given the exterior geometry with an horizon, basically there is a resilience of this geometry, which is intrinsic from the fact that there is inside or not singularity. It seems to say that it doesn't want to be destroyed, the black hole, right? Because if you have a spin care in a certain sense. So it's just a kind of, it can be said that it's a robustness theorem of black hole geometries, independently from the fact that there is, the motivation that you don't want to see naked singularity. There may not even be a naked singularity to be seen inside, but still it would work.
Yeah, no, it doesn't have anything to do with that. Of course, I mean, you should keep in mind that all we're doing is showing that a particular class of counterexamples fails,
that's true.
Which is a completely different story than showing that the black hole is actually stable and so on. I mean, which, a lot of work.
But it goes in that direction, let's say.
Yeah,
right?
yeah.
And it could be applied also to regular black holes.
Yeah,
that's interesting. Thank you.
Yeah, because otherwise, if when you can regularize the singularity in a way in which you're going to have new components of the stress and heat tensor at the horizon, but this can be made arbitrarily small. So if you had that change in behavior, that would be, as Stefan was saying, it would be kind of an instability, right? Essentially. So it's like, in that sense, one can understand this as some kind of stability with respect to doing these small changes on the horizon. Essentially, that's just because you can regularize the singularity in that way, right? I mean, it's like it's disconnected from the horizon. So there is a question from the attendees, I think, or not? I get a notification. No, from the panelists. This was Stefano, so I didn't see you before. That's why. Okay.
There is one question from Yong Gao.
Okay, didn't see it. I'm not very proficient at this. Let's see. I don't see it. I don't see it yet. So I see the. No, it's the hand raise, right? So I was just trying to find the question. Okay.
Can you hear me?
Yes.
Yeah, I have questions to Professor Eric Poisson. Yeah, so you mentioned that the tidal lab numbers of black holes become 0 in all the PM orders. So can we explain the tidal lab numbers of black holes become 0 because of the no-hair theorem?
Yeah, so there's certainly a connection between the two statements. So the no-hair theorem can be you can state it as saying that a black hole cannot support permanent multiple moments, and then that's an extension of that idea to the fact that even if you tidally perturb the black hole, then there will also be no tidal moments, no multiple moments generated from that. So yeah, so I think there's a connection, but it's not a direct, it's not a direct thing, because yeah, I mean, so there are some connections and there's some mathematical ones, and but I think that's the idea. So that regardless of what you do, the black hole will never support multiple moments.
So recently I found that there is a study called the spinning black holes fall in love. They calculate the tidal lab numbers of spinning curved black holes, and they came to the conclusion that the tidal lab numbers of curved black holes is not 0. So I'm wondering what's your comments on that work?
Right. So that's something that was raised previously. So somebody else asked a question about rotating black holes.
Yeah.
And so what I answered, so what I said is that, so there are two types of love numbers, ones that will affect the conservative aspects of black holes going around other bodies. And the other class affects dissipation across the event horizon. So the love numbers that were identified for rotating black holes are associated with dissipation. But you can also assign non-zero love numbers to Schwarzschild black holes and also connect them to dissipation. So the point is that because we have dissipation across the event horizon, we have, you can assign love numbers to that effect, which has nothing to do with, tidal interactions as they're normally understood in, Newtonian physics. So it really has to do with the dissipation or the heating of the black hole by absorption.
Okay, I see. Thank you.
Okay, so I think we can wrap it up because it's about time. So I would like to thank the 3 speakers for the really nice talks and for being here for the discussion.